Imagine a silent night on Mars, a canvas of deep black broken only by the cold, distant glow of constellations unfamiliar to our terrestrial sky. The red planet's horizon lies still, desolate, and apparently untouched by anything that does not belong to the solitary, cold mechanics of the solar system. The year is 2025, specifically the month of October, a period marked by routine data collection from the robotic explorers humanity has dispatched to the fourth planet. This is a time of quiet scientific work, measuring seismic activity, analyzing atmospheric dust, and, most importantly, examining the composition of ancient Martian rocks. The Perseverance rover, our most advanced mobile laboratory, is diligently focused on its geological tasks, its sophisticated camera systems sweeping across the Jezero crater in search of biosignatures, remnants of life that might have existed billions of years ago. The universe, it seems, is proceeding according to predictable, well-calculated order. Then, that silence is abruptly broken. A single, impossibly thin line of light, a razor-sharp thread, cuts across the Martian darkness. It is an intrusion, an unmistakable sign that something utterly foreign has arrived. This streak is not a meteor, which would appear as a violent, incandescent flash of burning debris. It is not a random cosmic ray strike, which would register as a static, isolated point of energy. Instead, this light is deliberate, focused, and utterly precise. The object generating this faint luminescence is moving at a staggering velocity, nearly 60 kilometers per second, a speed that dwarfs any object native to our local gravitational system. Frame by frame, the path of this intruder is documented, a perfect, unbroken trajectory across the star field. And, critically, this observed streak matches, with almost surgical precision, the predicted path of a celestial object known to astrophysicists as 3I/Atlas. Atlas is not from our solar system. It is an interstellar visitor, an object born between the stars, a rogue traveler crossing the immense gulfs of the galaxy. Its arrival was known, its trajectory calculated, but its actual capture in an image was a long shot. The sheer magnitude of this moment cannot be overstated. A piece of the cosmos, forged in a distant, unknown stellar nursery, was gliding silently past Mars, captured by a machine designed to look at the ground. The initial data, raw and unpolished, arrived back on Earth, a simple file among thousands of routine engineering logs. This revelation, this faint streak on a Martian sky, marked the definitive, undeniable convergence of two colossal truths: the vastness of the universe and persistent, relentless curiosity of humanity. The image was a whispered galactic movement, a sudden, blinding awareness that our solar system is not a closed system, but an open corridor through which interstellar objects freely wander. And yet, this profound discovery did not enter the public sphere through the usual channels of government agencies or major scientific institutions. It began instead as a quiet, digital tremor originating not from the halls of NASA, but from the patient work of a lone geophysicist on Earth. The captured light, the speed, the trajectory, it all pointed to Atlas, and it pointed to a revolution in how humanity observes its cosmic neighborhood. This single observation, this fragile line of light, redefined not only what we were capable of seeing, but who held the power to see it. It was the universe providing a riddle, and a solitary human being, armed only with mathematics and belief, was the first to recognize a language in which it was written. The moment of discovery for the interstellar object 3I/Atlas did not arrive with a fanfare of official press releases or a carefully choreographed data briefing from the high offices of NASA. Instead, it emerged from persistence and independent effort of a single individual, Stephen Burns, a lone geophysicist driven by a conviction in the power of open data. Burns was a man whose arsenal consisted not of billion-dollar space telescopes or deep space arrays, but of patience, mathematical rigor, and an unwavering belief that scientific truth should not be gated behind institutional walls. His focus was fixed not on the next big government grant, but on extracting extraordinary revelations from publicly available, mundane datasets. The crucial source material for his breakthrough was surprisingly humble. 9 minutes of raw footage streamed from the Perseverance rover, a robotic explorer fundamentally designed to examine Martian geology, not deep space phenomena. These cameras, intended to analyze the texture of Martian rocks and the composition of ancient riverbeds, suddenly became the most critical instrument for interstellar observation. Burns embarked on a forensic, pixel-by-pixel investigation of the raw footage. His task was a masterclass in meticulous data processing. First, he had to calibrate each frame against known star positions and distant constellations to establish a precise geometric reference. Then, he corrected for every conceivable optical distortion inherent in the rover's lens system. Next, he synchronized the timestamps on the footage to atomic precision, a necessary step for tracking an object moving at relativistic speeds. Finally, and most critically, he began the process of noise subtraction. This involved computationally identifying and removing every source of interference. The steady glow of distant galaxies, the faint light from Jupiter, stray digital compression artifacts, and ubiquitous hits from random cosmic rays. What remained after this painstaking, multi-layered process was a thread of light so faint it bordered on invisibility, a razor-thin, unbroken streak. This streak was the ghost of 3 Atlas. It was too consistent to be a glitch, too fast and linear to be space debris, and perfectly, mathematically aligned with the most current orbital models of the interstellar trajectory. Burns's reaction to this definitive confirmation was not to rush to a major journal or contact a high-profile news outlet. He did something genuinely radical, something that challenged the established institutional model of scientific discovery. He released everything: the raw image files, the complex processing script he wrote to filter the noise, and even the intermediate image stacks for anyone, anywhere to download, examine, and verify. This was a transparent invitation to the global community, a digital gauntlet thrown down for scientific reproducibility. By placing the undeniable evidence and the means to verify it directly into the public domain, Stephen Burns transformed a lone observation into a collective, planetary quest. He demonstrated that in the age of open data, the first crucial glimpse of an object born between the stars could emerge not from the exclusive halls of power, but from a citizen-scientist collaboration across the open servers of the Internet. This rogue revelation was not just about Atlas. It was about democratizing the very act of universal discovery. Stephen Burns' release of the raw Mars rover footage and his processing code was more than a mere data dump. It was a detonation of scientific protocol, initiating a genuine data democracy that fundamentally redefined the process of cosmic discovery. In an era where vast amounts of scientific data, especially from high-profile space missions, are often sequestered for months or years behind institutional firewalls for exclusive analysis by a privileged few, Burns' radical transparency was an explicit and powerful invitation to the world. He threw open the doors of the digital laboratory, transforming the pursuit of the interstellar object Atlas from a governmental project into a massive, crowdsourced planetary experiment. The effect was immediate and viral. Within hours of the data going live, the raw frames and the Python script began to ripple across the Internet like an electric current coursing to the global scientific brain. Thousands of analysts, astronomers, both professional and amateur astrophysicists, and even dedicated hobbyists, anyone with a computer and image processing software, downloaded the files. The intellectual labor of verification and analysis was instantly distributed across continents and time zones. The universe was no longer being studied exclusively in heavily guarded university laboratories or classified observatories. It was being dissected in real time in home offices, suburban garages, remote cabins, and dorm rooms across the planet. This was discovery unfolding in the most public and collaborative manner imaginable. The shared servers and public forums became the new scientific peer-reviewed journals. Data was constantly cross-examined, criticized, and independently verified. The global curiosity effectively became the shared instrument of discovery. Every user running Burns' script or their own custom algorithms was participating in a colossal live scientific confirmation attempt. The core question echoed everywhere. Was the streak real, This democratization of discovery was driven not by profit or institutional mandates, but by the purest form of human motivation, curiosity. It fostered an environment of scientific chaos, a beautiful, productive chaos where every result was instantly scrutinized. This open approach served two critical functions. First, it accelerated the process of verification far beyond the capacity of any single institution. The collective computing power and diversity of analytical approaches guaranteed that the faintest signal would not be missed, nor would a digital artifact be mistaken for a genuine cosmic event. Second, it fundamentally established the credibility of the finding from the outset. Because the data had been verified and reproduced thousands of times by independent global teams, the eventual scientific consensus will be nearly unbreakable, built on a foundation of radical transparency. Burns had effectively bypassed the traditional, often slow and exclusive, path to astronomical validation. By inviting the entire world to participate in the search for Atlas, he ensured that humanity's first solid glimpse of an object born between the stars was a shared triumph, an extraordinary testament to the power of open collaboration in the modern age of science. The moment Stephen Burns releases raw image data and processing code, the investigation into 3i/Atlas ignited into a scientific wildfire, confirming profound efficacy of open data sharing. The challenge was massive: to reproduce, independently, a faint, almost imperceptible streak of light captured by a camera designed for geology, not deep space, traveling at an astonishing velocity. This was the ultimate test of Burns's initial claim and the first major stress test of the new, distributed model of scientific discovery. The global community eagerly accepted the challenge, transforming forums and shared data repositories into hyper-efficient digital laboratories. The wave of analysis was intense and multifaceted. Teams of analysts, ranging from seasoned professional astronomers to graduate students and dedicated hobbyists with advanced image stacking skills, downloaded the vast files. They fired up their image processors, custom-built algorithms, open-source tools, and commercial software, and began the laborious task of peeling back the cosmic layers. Every known technique in image processing was applied: aggressive stacking, high-pass filtering, geometric correction, and advanced noise modeling. The goal was to isolate the signal of Atlas from the overwhelming background noise of cosmic rays, hot pixels, and digital compression artifacts. After days of painstaking, often frustrating work, many independent analysts began to report success. Across different platforms, using different methods, teams were able to reproduce the exact same faint streak that Burns had initially documented. This independent, multi-source confirmation was the gold standard of scientific validation. The streak was consistent, impossibly thin, and perfectly aligned with the predicted orbital trajectory of 3i/Atlas. The verification was not a singular event, but a continuous flow of successful reproductions, creating an overwhelming weight of evidence. The intensity of the investigation led some teams to push the limits of the data even further. Reports began to surface claiming to have glimpsed additional hairline traces in image sequences captured slightly later than Burns's initial frames. These claims suggested the presence of smaller, faster companions darting alongside the main object. The implication of this was staggering. If these secondary traces held true, Atlas was not merely a lone traveler, but potentially part of a coordinated swarm or an interstellar convoy gliding past Mars. This possibility instantly amplified the mystery, transforming a single comet into a potential fleet. However, the scientific wildfire was also met by the lifeblood of science: fierce skepticism. Many rigorous researchers found nothing but noise, reporting only the random statistical mirages born from overly aggressive stacking techniques or digital artifacts generated by pushing compression limits of the images. Accusations arose that enthusiasts were engaged in pattern recognition, seeing faces in clouds of data, mistaking the artifacts of their own algorithms for signs of intelligent design or structural complexity. The forums turned into a continuous, passionate debate over the nature of truth in the age of data, a planetary experiment where the only shared instrument was curiosity itself. The collective effort was a testament to the democratization of discovery, proving that a universe's riddles could be dissected openly and collectively. The scientific wildfire sparked by the Atlas data immediately triggered the fiercest battle in modern astrophysics. The intense debate between identifying a genuine signal from the stars and dismissing what might merely be a digital artifact of our own instruments and processing. This dichotomy is at the heart of all great discoveries. But for 3i/Atlas, the intensity of the open data scrutiny pushed this debate into the public domain with unprecedented speed. The shared servers and forums quickly became a polarized digital arena where the desire for cosmic revelation clashed violently with the imperative for scientific rigor. On one side stood the enthusiasts, often led by the sheer excitement of confirming an interstellar visitor and pushing the limits of the available data. They pointed to the reproducibility of the main streak, the statistical unlikeliness of its perfect orbital alignment, and the tentative sightings of companion objects as evidence that Atlas was more than just a typical comet. For them, the tiny imperfections and faintness of the signal were simply proof of the object's immense distance and velocity, requiring aggressive image stacking and filtering to reveal the hidden truth. They accused skeptics of lacking imagination or being bound by institutional fear, reluctant to accept a paradigm-shifting observation that came from outside official channels. On the opposing side stood the skeptics, usually comprised of professional astronomers and physicists trained to prioritize false positive avoidance above all else. They found plenty of ammunition for doubt. They pointed to the inherent limitations of the Perseverance rover's cameras, which, being designed for geological close-ups, introduced significant noise and distortions when pointed at the blackness of space. Many analyses failed to reproduce the streak at all, or only managed to do so by applying filters so aggressive they risk creating statistical mirages, patterns that appear significant but are mathematically random. The purported companions were often dismissed as simple digital compression artifacts, where the image data broke down under intense manipulation, or as random cosmic ray strikes that were erroneously linked by overzealous stacking algorithms. For the skeptics, extraordinary claims required extraordinary evidence, and a faint streak of a few pixels from a non-specialized camera was, by definition, not extraordinary enough. The forums became a crucible of debate, a transparent display of the scientific process in action. Data was downloaded, recalibrated, stacked, filtered, and unfiltered 1,000 different ways. It was a rigorous, collective exercise in debunking one's own assumptions. The core of the argument moved beyond simple pixels and noise. It became a debate about the very nature of scientific truth in the age of democratized data. How much evidence is necessary to overturn a foundational assumption of astrophysics? Was the signal a genuine whisper from the universe, or a digital ghost conjured by the desperation to find evidence of the extraordinary? The tension between wonder and rigor was palpable, leaving humanity suspended in a state of electric uncertainty, knowing that somewhere within those millions of frames, between the undeniable noise and the faint signal, lay the answer to the deepest question the species has ever asked. Are we truly alone? Just as the global debate raged over the certainty of the primary streak, a new, more perplexing piece of evidence emerged from the deep data. A brief, spectral pulse of green light that flickered across the Martian sky. This was not the faint, linear movement of the object itself, but a singular, luminous flash, a spectral whisper that occurred just 3 seconds past midnight on October 3rd, within one of the stacked image sequences. For those meticulously tracking the orbital geometry of 3i/Atlas, this fleeting shimmer immediately ignited one of the most intense and complex scientific debates of the entire investigation. The question was immediate and profound. Was this flash real or merely a digital illusion, a ghost conjured by the aggressive processing required to find the main signal? In classical comet science, a green glow is ordinarily no mystery. It is a reliable, well-understood chemical signature. When comets approach the sun, their frozen components sublime, and the resulting gas molecules are excited by ultraviolet radiation. Specifically, diatomic carbon molecules, C2, emit light at specific, recognizable wavelengths, around 516 and 563 nanometers, producing the signature green haze common to many comets. It is a cosmic fingerprint, a guaranteed chemical rule. But with Atlas, the established chemistry refused to cooperate. This green flash became an anomaly of the highest order. If it were a natural cometary glow, it should be accompanied by the telltale spectral readings of the associated molecules. Yet, early spectra transmitted back from the Mars flybys suggested an object with peculiar composition, an atmosphere rich in carbon dioxide, strangely depleted in water vapor, and, critically, almost devoid of the carbon chain C2 that should have produced the green glow in the first place. A comet that glows in a color forbidden by its own chemistry is a profound contradiction. It is like hearing music from a soundlessly played instrument. The scientific community immediately split over the cause. Some rigorously argued it was a simple cosmic ray strike, a single high-energy particle slamming into the rover's detector, which was then amplified into a dramatic flash by the necessity of image stacking. Cosmic rays are common and often mimic genuine astronomical signals. Others fiercely countered that the timing and position of the flash were too perfect to be random. The green light occurred precisely when and where 3I/Atlas was predicted to be, matching the geometric path of the interstellar visitor to within arcseconds of precision. This geometric coincidence made the simple cosmic ray explanation highly problematic. Without the original calibrated FITS files or the highly detailed camera telemetry from the rover, achieving definitive certainty remained an impossible reach. The silence from official sources, bound by the need for absolute, repeatable verification, only intensified the mystery. The deeper question lingered beneath the noise of the debate. If the light was indeed real, what kind of matter, originating from an unknown stellar system, glows green without the presence of carbon? This fleeting shimmer became more than a mere data point. It became a powerful symbol of scientific humility, whispering that perhaps, hidden within that momentary flare above Mars, lay the first subtle signs of a chemistry entirely not born of this solar system. The perplexing event of the green flash introduced the concept of forbidden chemistry into the Atlas investigation, posing a monumental challenge to established cometary science. The established rules of the cosmos dictate that when sunlight excites the volatile materials escaping from a comet's nucleus, the resulting glow, particularly the green light, is a reliable spectral signature of diatomic carbon, C2, and other simple carbon chain molecules. This is a foundational concept in astrochemistry, a universally accepted fingerprint of cometary activity. Yet, the data from 3I/Atlas shattered this expectation entirely. The early spectra gathered from the Mars orbiters revealed an object that was behaving like a comet while simultaneously denying the chemistry required for that behavior. The atmosphere, or coma, surrounding Atlas was found to be strikingly rich in carbon dioxide, $CO_2, a compound that produces ultraviolet emissions, not green light. But critically, it was strangely depleted of water vapor, $H_20, and almost entirely devoid of the C2 and C3 carbon chains. If the object possessed so little of the expected C2, why did the image stacks reveal a green flash? Even a fleeting one. This was the core paradox. Atlas was playing music that its instrument lacked the strings to produce. The lack of water vapor was, in itself, a significant anomaly. Most comets are essentially dirty snowballs, icy fragments of the outer solar system, and their activity is dominated by the sublimation of $H_20. Atlas's preference for outgassing $CO_2 and its apparent dryness suggested an object formed under highly exotic conditions, perhaps in a region of a foreign solar system where water ice was scarce, or in a cold, deep part of the interstellar medium, where $CO_2 was the dominant volatile. This unusual mix hinted at a birthplace fundamentally unlike the one that spawned our own solar system's comets. But the most frustrating contradiction remained the green light. If the light was genuine, its origin had to be attributed to an unknown chemical process or a molecule not previously associated with cometary glow. Researchers were forced to speculate wildly. Could the light be produced by complex metallic oxides or exotic silicon compounds? Could it be a transient emission from an entirely new molecular structure forged in the intense, high-energy environment of the interstellar void? These questions push the boundaries of known physics and chemistry, forcing scientists into a humbling state of intellectual uncertainty. The green flash, therefore, became the symbol of a cosmic riddle. Either the light was a profound digital error that fooled thousands of analysts, or it was the first subtle piece of evidence for a chemistry not born of the solar system. In science, such anomalies are the cracks through which the light of discovery escapes. They indicate that the universe is under no obligation to conform to our expectations, and that within the spectral data of 3I/Atlas, humanity might have glimpsed a truth about matter that our terrestrial models are not yet wise enough to explain. The mystery of the green flash distilled the entire Atlas investigation into a battle over a single pixel and 3 seconds of time, forcing the scientific community into a high-stakes debate between the mundane explanation of a cosmic ray strike and the extraordinary possibility of a cosmic coincidence. For such a fleeting, minuscule piece of evidence, the implications were enormous, potentially leading either to a genuine scientific revolution or to a complete retraction of the initial claims. The argument for the cosmic ray explanation was strong and rooted in probability. The rover's camera sensors are constantly bombarded by high-energy particles from space. When one of these particles strikes a detector, it generates a bright, localized flash of light that can easily be misidentified as an astronomical event, especially when the image is aggressively stacked and processed for enhancement. For many rigorous analysts, the green flash's brevity, lasting less than a heartbeat, and its isolated nature made it the perfect candidate for an amplified cosmic ray hit. This explanation was physically plausible, statistically frequent, and required no paradigm-shifting assumptions about alien chemistry. However, the counter-argument for a cosmic coincidence rested entirely on geometric improbability. The flash occurred exactly when and where the interstellar object 3I/Atlas was predicted to be, matching its trajectory and the orbital geometry of the Martian camera to within an arcsecond. For the flash to be a random cosmic ray, that ray would have to strike the precise pixel corresponding to the predicted location of the object at the precise moment the camera was exposed. This confluence of timing and geometry, occurring at the moment of peak interest in the object, made the random chance explanation feel deeply unsatisfying and statistically unlikely to many researchers. The fight over this single pixel transformed online forums into digital trial chambers. Teams meticulously rechecked their synchronization, attempting to determine if a slight timing error or a tiny misalignment in the image stacking process could have artificially centered the random ray hit onto the Atlas trajectory. Without the original calibrated data, certainty remained elusive. Reproducibility was also inconsistent. Some groups could reproduce the flash effect using the released data, while others rigorously failed, finding only noise or artifacts. This tension highlighted a fundamental challenge in modern science, separating true signal from instrument noise, especially when the signal is at the absolute limit of the instrument's capability. The debate was about more than just a flash of green light. It was about the standards of evidence required for a truly paradigm-shattering discovery. Should one prioritize a conservative, statistically safer cosmic ray explanation, or follow the tantalizing thread of geometric coincidence that pointed toward an unimaginable truth? In the end, the question remains a silent, haunting testament to the limits of our current observational certainty, an enduring paradox born from a solitary, unexplained pixel. The observation of 3I/Atlas in October 2025 was a triumph of orbital mechanics and happenstance, as the geometry of the cosmos conspired to make Mars our only functional observer. For the first time in human history, an interstellar object was being observed not from Earth, but from another planet, a necessity dictated by the crippling reality of our own orbital position. Atlas's trajectory brought it close to the Sun during its peak observation window, rendering all Earth-based telescopes, from the largest ground observatories to the Hubble and James Webb Space Telescopes, effectively blind. The sun's intense glare and the massive storm of solar radiation rendered Earth-based observation impossible. Any attempt to aim a sensitive instrument anywhere near the solar disk would result in immediate blinding or catastrophic damage to the detectors. To observe Atlas, humanity needed a vantage point far away from the blinding light of our star. Mars, positioned at a distance and angle relative to the sun that provided a clear, dark view of the comet's trajectory, provided that critical second pair of eyes. This reliance on our neighboring planet placed the burden of observation entirely on the existing fleet of robotic sentinels orbiting the red planet. NASA's Mars Reconnaissance Orbiter, MRO, the European Space Agency's Trace Gas Orbiter, TGO, and Mars Express. This presented an immense challenge, as these spacecraft were never designed for this task. Their primary directives are to photograph Martian geology, sand dunes, canyons, atmospheric frost, and trace gases. They are geological paparazzi, not deep space astronomical cameras. Repurposing them for interstellar observation required a level of surgical precision in orbital maneuvering and timing that tested the limits of engineering. Each orbiter had to pivot drastically away from its normal orientation, temporarily abandoning its primary scientific goals to point its instruments into blackness of space. The exposure timing had to be calculated with second-to-second exactitude. A shutter trigger deployed a fraction too early, and Atlas would be outside the narrow field of view. A fraction too late, and the fast-moving cosmic visitor would already be gone, lost forever against a vast star field. Every frame taken was a high-stakes gamble, and every pixel was a potential revolution in astrophysics. The mission was not a traditional astronomical campaign. It was a testament to the ingenuity and rapid adaptability of the orbital mechanics teams at NASA's Jet Propulsion Laboratory and the ESA. They worked around the clock, refining Atlas's projected path daily, accounting for every known gravitational, radiative, and relativistic perturbation. On paper, this was the most coordinated interplanetary imaging campaign ever attempted for a non-human object. It underscored profound reality that to truly understand the universe beyond our solar system, humanity must learn to look outward not just from Earth, but through the many eyes it has placed across the solar system's dark corridors. Mars, the silent sentinel, became the keyhole through which humanity gained its most intimate glimpse of a visitor from between the stars. The campaign to image 3i/Atlas from Mars was a delicate, high-wire act of engineering and mathematics, a walk on the orbital tightrope, where success hinged on microsecond timing and millimeter precision. The sheer difficulty of the task was rooted in the extreme nature of the object itself. An interstellar visitor racing to the void at a blistering 200,000 kilometers per hour, forcing existing Mars orbiters, instruments designed for slow, fixed-target observation, to perform a task completely outside their operational parameters. The core challenge was one of timing and angular velocity. Standard astronomical telescopes on Earth track objects by compensating for the Earth's rotation and the object's slow relative movement. The Mars orbiters, however, had to account for their own velocity and the extreme velocity of Atlas, which meant the object was streaking across the camera's field of view at terrifying angular speed. To get a sharp image, the exposure time had to be incredibly short, yet a short exposure time meant the signal, the faint light from the comet's coma, would be too weak to detect. The engineering teams had to find a perilous balance: long enough exposure to capture light, but short enough to prevent the streak from blurring into an unrecognizable smear. Furthermore, the physical maneuvering of the orbiters was complex. Spacecraft like the Mars Reconnaissance Orbiter, MRO, used thrusters and reaction wheels to maintain their orientation. To pivot the high-resolution camera, HiRISE, toward a point in the blackness required precise, delicate shifts in attitude. These shifts consumed valuable fuel, and the constant reorientation created vibrations that could easily ruin the fragile exposures. Orbital mechanics teams worked feverishly to program cued stare sequences, instructing the orbiters to predict Atlas's position and stare at that point in the void for the exact millisecond it was predicted to pass through the field of view. The data had to be calculated and recalculated daily. factoring in minute gravitational perturbations from Jupiter and the Earth, solar radiation pressure acting on Atlas, and even the subtle relativistic corrections necessary for high-velocity tracking. The entire operation was a testament to the sophisticated mathematics underpinning modern space travel. Every single exposure was a high-stakes bet, the result of thousands of hours of computational refinement. The stakes were enormous. A successful capture would yield the first direct, close proximity images of an interstellar body near another planet, providing data that could fundamentally revolutionize astrophysics. A failure, on the other hand, meant the entire brief, critical window for observation would be lost forever. The silence that followed the imaging campaign, the lack of immediate data releases, was not proof of conspiracy, but an eloquent testament to the immense scientific integrity demanded by the difficulty of the task. The imaging teams, aware of the magnitude of potential discovery, were forced to check, recalibrate, and second-guess every single pixel, caught in the tension between humanity's powerful instinct of wonder and the cold, hard rigor of scientific certainty. Following the intense, high-stakes imaging campaign by the Mars orbiters, the world waited with collective, agonizing anticipation for the data. The scientific community and the general public, now fully engaged to the open data movement, hungered for the first official image, the definitive streak, the confirmation of the close encounter. Yet, days turned into a week, then 10 days, and all that emanated from NASA's Jet Propulsion Laboratory, JPL, was a profound, deafening silence. In the age of instantaneous communication, where images from Mars often arrive within hours, this void was not only unusual, but immediately fueled a scientific controversy and a wildfire of speculation across the internet. Was NASA hiding something? Had the data revealed evidence too extraordinary to release? Had the complex orbital choreography failed completely? The truth, as often happens in high-level scientific investigation, was far more nuanced, subtle, and profound than any simple conspiracy theory. The silence was not an act of concealment, but an eloquent testament to the rigorous, absolute demands of scientific integrity, the critical necessity of verifying data beyond any shadow of a doubt before public release. The imaging teams at JPL face a terrifying paradox of their own creation. The faint streak of the fast-moving interstellar object, if captured, looked virtually identical to the kind of electronic and cosmic noise their highly advanced processing algorithms were specifically designed to identify and erase. The genuine signal was perilously close to the false positive. The problem lay in the complexity of noise modeling and image stacking. To detect the faint light of Atlas against the vast blackness, the image teams had to layer and align dozens of exposures taken in rapid succession. This process, while essential for boosting the signal-to-noise ratio, introduced dangerous variables. Misalign an image stacked by even a fraction of a pixel, and the combination of background stars, cosmic ray hits, or simple hot pixels could conjure a phantom streak, a line of light that never existed in reality. Conversely, if the algorithms were too conservative, if the noise filters were too aggressive in their caution, they risked obliterating the very genuine signal they sought to find. The risk of announcing a paradigm-shifting discovery based on a digital ghost was an institutional fear that outweighed any pressure for a quick public announcement. Thus, the teams were locked in a cycle of meticulous re-verification. They checked, recalibrated, and second-guessed every single frame, every stacking parameter, and every noise subtraction technique. They had to prove, with statistical certainty, that the potential streak was geometrically consistent, temporally stable, and reproducible across different orbital instruments. Scientific integrity demanded this level of rigor. The world hungered for wonder, but the scientists demanded certainty. In that quiet, prolonged tension between universal revelation and analytical restraint, the scientific process itself was revealed, a discipline forever caught between the exhilarating possibility of a new discovery and the solemn responsibility of absolute truth. The JPL void was, paradoxically, the loudest statement of how seriously the scientists took the reality of Atlas. The spectral data transmitted from the Mars orbiters, once painstakingly processed and released, introduced an entirely new and deeply unsettling category of anomaly: the peculiar and contradictory chemical fingerprint of 3I/Atlas. Comets, as a general rule, are expected to be predictable chemical machines, icy remnants from the outer reaches of their solar systems, composed primarily of water ice, carbon monoxide, and various carbon chain molecules. Their activity is almost always dominated by the sublimation of water vapor, $H_20, which forms a large, visible cloud of gas and dust. Atlas, however, broke this rule entirely, presenting a composition that defied the very definition of a conventional comet. The spectrometers on board the orbiters reported an atmosphere, or coma, that was surprisingly rich in carbon dioxide, $CO_2, yet strikingly barren of water vapor. While $CO_2 is a known component of comets, its dominance over $H_20 is extremely rare, usually seen only in the most distant cold comets, or those that have made so many passes near the sun that their surface water has been completely depleted. For an interstellar visitor, presumably making its first ever passage through the inner solar system, this dryness was deeply puzzling. It suggested two radical possibilities. Either Atlas originated from a stellar system where the planet-forming environment was fundamentally different from ours, specifically one where water ice was scarce, or that Atlas had been thermally processed in a way that had efficiently driven off its water content long before it reached our region of space. The scientific implications of this chemical anomaly are enormous. The composition suggests a birthplace environment that fundamentally challenges our current models of star and planet formation. Our models assume that water ice is a universal building block in the cold, dense regions of stellar nebulae. Atlas, with its strange richness in $CO_2 and scarcity at $H_20, hints at the existence of chemically distinct stellar nurseries throughout the galaxy. It suggests that there are regions where the chemical pathways for forming volatiles differ profoundly, creating objects that are exotic even before they begin their interstellar journey. Furthermore, this dryness feeds directly back into the mystery of its activity. If Atlas lacks the easily sublimated water ice, the source of its observed outgassing, the very activity that makes it look like a comet must be the $CO_2 and other more refractory volatiles. This requires the nucleus to be warmed more significantly than a water-dominated comet to sustain the same level of activity. The chemical anomaly, therefore, is not a mere detail. It is a fundamental challenge to the classification of Atlas. It suggests that this object might belong to an entirely new category of celestial body, an interstellar dry comet, an object forged in the heat or cold of an alien system, forcing humanity to confront the reality that the most basic chemical rules of the universe might not be as universal as we once assumed. By the end of 1943, the mood inside the professional officer corps had undergone a complete and irreversible transformation. The early arrogance of 1940 and the stubborn denial of 1942 had been completely purged, replaced by a pervasive, chilling sense of quiet fatalism. The war, they understood, was not just strategically lost. It was now a countdown to national destruction. This was not an emotional collapse, but a professional conclusion drawn from irrefutable facts and figures that Hitler refused to acknowledge. The military professionals were grounded in the reality of numbers and resources. They saw that German industry could no longer replace the devastating losses of manpower and material on the Eastern Front. They witnessed the Allied bombers, now virtually unopposed, ruling the skies over Germany, systematically dismantling the infrastructure and industrial capacity that was supposed to fuel the war effort. They tracked the decimation of the U-boat fleet in the Atlantic, which meant the vital supply lines from the United States to Britain and the Soviet Union could no longer be severed. The generals could read the maps and the production charts. They were no longer fighting for victory, but for survival, and the odds were zero. This fatalism manifested in two divergent, equally dangerous paths. For the vast majority, it meant embracing a stoic, cynical silence. They chose to maintain the facade of loyalty and duty, rationalizing their compliance as necessary to prevent a total collapse and preserve some semblance of order in the chaos. They continue to issue and obey orders, even impossible ones, telling themselves that perhaps a political miracle, a rift between the Western Allies and the Soviet Union, might yet occur. This silence was born of fear. Fear of the Gestapo, fear of execution, and a deeply ingrained fear of violating the sacred oath of military obedience. They became masters of falsifying reports, subtly adjusting casualty figures and equipment statuses to mitigate the worst of Hitler's destructive commands. However, for a significant courageous minority, the grim certainty of defeat led to the most extreme act of conscience, contemplating the unthinkable. These were not merely disgruntled idealists. They were professional soldiers who, having calculated the mathematical inevitability of annihilation, concluded that Hitler was the singular factor preventing an armistice and ensuring Germany's total ruin. Men like General Ludwig Beck, Henning von Treschow, and Colonel Claus von Stauffenberg reasoned that to remove Hitler was not an act of treason, but a final, desperate act of military duty, the only means left to save the Wehrmacht and the German nation from being destroyed alongside the regime. By late 1943, the seeds of the July 20th plot were finding fertile ground within an officer core paralyzed by dread and consumed by a fatalistic certainty. The chemical paradoxes of 3 Eyes/Atlas were soon compounded by equally baffling dynamic anomalies, observations that directly challenged the fundamental laws of celestial mechanics as applied to comets. As the Mars orbiters monitored the object, they detected evidence of outgassing activity, the faint cloud of gas and dust that defines a comet. However, one specific observation defied conventional dynamics: the presence of sharply defined sunward jet, often referred to as an anti-tail. Comets, according to physics, outgas primarily when the sun's heat causes volatiles to sublimate. The resulting jets of material typically push the comet away from the sun, creating the characteristic tail that trails behind it. For an anti-tail or a jet pointing directly toward the sun to exist without instantly being distorted by solar wind and radiation pressure, it would require an immense, stable force. If the jet was due to outgassing, the physics dictates that the resulting recoil should dramatically alter the object's trajectory, causing it to dance erratically through space, a phenomenon known as non-gravitational perturbation. Yet, this is where the dynamic paradox of Atlas emerged. Despite the evidence of sharp, sunward jet, the analysis of its trajectory showed that Atlas was gliding with serene, almost supernatural precision. It maintained the calm, steady inertia of a massive, dead asteroid. There were no detectable perturbations, no course deviations, and no measurable recoil from its own outgassing. It was, in effect, simultaneously chemically alive, showing signs of volatile release, and dynamically dead, unaffected by the forces that should accompany that release. This contradiction cut to the very core of celestial mechanics. A comet that active, with such a sharply defined jet, should be nudged and jostled through the void. The fact that Atlas moved with such precision suggested one of two radical possibilities. Firstly, its nucleus must be massive, perhaps composed of highly dense, refractory material weighing tens of billions of tons, giving it sufficient inertia to resist the recoil. This would contradict the initial brightness estimates of the object, which suggested a much smaller size. Secondly, and far more provocatively, it raised the question that some researchers began to whisper in guarded tones. Was this object controlling its own motion? Could the outgassing be symmetrical and precisely timed, effectively canceling out any net thrust and allowing the object to glide with artificial precision? While the latter idea risks crossing the line into speculation, the data itself demanded that the model must bend. Conventional cometary models could not explain the coexistence of a sunward jet and a gravitationally pure trajectory. Atlas, in its simple flight through the solar system, served as a profound anomaly, forcing astrophysicists to question whether the familiar, chaotic dynamics of our solar system's comets applied to these enigmatic wanderers from interstellar space. The object that burns like a comet and moves like an asteroid stands as a paradox incarnate. Sometimes the universe presents coincidences so exquisitely precise, they feel like deliberate cosmic signals. When a Harvard team, led by astrophysicist Avi Loeb, traced 3i/Atlas's trajectory backward through space and time, they stumbled upon one of those calculated alignments, the kind that forces even the most dedicated rationalist to pause and consider the philosophical edge of science. Their calculations suggested that millions of years ago, the path of this interstellar object crossed a tiny patch of sky, holding a near-mythic status in the annals of astronomy, the coordinates of the 1977 WOW signal. The WOW signal was a powerful, 72-second-long narrowband radio burst detected by Ohio State's Big Ear Observatory, centered precisely on a hydrogen line frequency of 1,420 megahertz. This frequency is considered a cosmic common channel, a universal, quiet channel that any intelligent civilization might use to announce its presence. Nature does not typically use this exact frequency with such intensity and duration. For nearly half a century, the signal has been an enduring mystery. The transmitter, if one existed, vanished into history, never to be heard from again. Loeb's team discovered that Atlas just happens to trace a trajectory that, when projected backward to the vast reaches of space and deep into the geological epochs, passes alarmingly close to the specific celestial coordinate from which the WOW signal originated. The odds of such an alignment occurring purely by random chance were calculated to be incredibly low, roughly 0.6% according to Loeb's initial analysis. Unlikely, yes, but certainly not impossible. Skeptics were swift to point out the scientific pitfalls. Positional uncertainties compound exponentially across interstellar distances and epochs. A deviation of a few arcseconds today could translate to millions of kilometers of error in the distant past. They accuse Loeb's team of post hoc reasoning, finding patterns after the fact and mistaking them for intentional design. The analysis, critics argued, crossed the line from physics into pattern seeking based on confirmation bias. Yet, even the most rigorous skeptics could not entirely dismiss the haunting elegance of the alignment. If an intelligent civilization wished to draw attention to a specific location in the sky, the hydrogen line would be the most rational, universal beacon, and an interstellar probe passing near that same coordinate millennia later would provide an undeniable signature. Coincidence or continuity? This is where wonder meets discipline. The alignment doesn't prove communication, but it does raise a powerful question that pierces the boundary between astronomy and philosophy. Whether the WOW signal was a message but a map? If that were true, 3i/Atlas might not merely be a wandering comet. It could be a messenger following trajectory written into the heavens long before humanity learned to listen. The alignment is a reminder that the universe is far more imaginative than our current models allow for. The calculus of coincidence aligning 3i/Atlas with the 1977 WOW signal transcends mere statistical analysis. It pushes the investigation into the realm of philosophical inquiry, forcing a profound contemplation of the boundary between natural phenomenon and deliberate communication. The alignment compels us to ask, what constitutes evidence of intelligence when the time frame spans millennia and the distance covers light years? Is our current understanding of physics and astronomy equipped to distinguish between an exquisite natural coincidence and a deliberate interstellar signature? The very possibility that the WOW signal, that isolated, powerful, narrowband burst, could be linked to an interstellar object that happened to visit our system decades later demands a reassessment of the signal's nature. For years, the signal was viewed as a potential message, a transient communication attempt from a long-vanished transmitter. But the Atlas alignment suggests a far more intriguing possibility. The signal might have been a map or a marker, a beacon placed in the cosmic dark to denote a point of interest or a path for an ongoing expedition. If the signal was a map, then the coordinates marked the starting point or the destination of an interstellar probe launched by a civilization millions of years ago. The probe, now known as Atlas, would simply be following that ancient, predetermined trajectory. This narrative suggests a technological capability and a sense of deep time, a galactic continuity, that utterly dwarfs human endeavors. It moves the entire discussion away from a search for communication and into a search for relic technology drifting across the galaxy. The ethical dilemma for scientists is immense. Scientific discipline demands that they must exhaust every natural explanation, instrument error, statistical anomaly, and pure chance, before even whispering the word artificial. Yet, history is replete with examples where a staunch adherence to the prevailing paradigm blinded researchers to revolutionary truths. The Atlas-Wow alignment, however weak in statistical terms due to compounding errors over time, provides a perfect example of how the universe might offer a hint that is mathematically faint but philosophically overwhelming. This convergence of astronomy and philosophy asks humanity to stretch its imagination. If the alignment holds, it suggests that the universe has a much richer, more deliberate history than we currently record. It invites us to consider that Atlas might be more than an icy rock. It could be a messenger following trajectory written into the heavens long before human civilization began. For now, the scientific community holds the question gently, refusing to give in to fantasy while simultaneously refusing to dismiss the profound symmetry. The ultimate truth, whether natural or artificial, promises to redefine humanity's place in the cosmos. Just as the mystery surrounding its chemistry, dynamics, and potential alignment with the WOW signal reached their fever pitch, the interstellar wanderer, 3 Eyes/Atlas, executed a calculated, inevitable maneuver. It vanished behind the sun. This was not a catastrophic event or a sudden disappearance, but a consequence of orbital mechanics. Atlas approached perihelion, its closest point to our star, and was promptly swallowed by the blinding brilliance of the solar glare. For 5 long, agonizing weeks, both Earth-based telescopes and the Martian orbiters were effectively blind. No instrument, no optical telescope, no radio dish, no space probe could pierce the storm of solar radiation that hid the object from view. This solar occultation was a necessary cosmic intermission, a forced pause in the frantic pace of discovery. While the physical object was temporarily invisible, the questions it left behind only burned brighter, creating a period of intense intellectual activity and nervous anticipation among astronomers worldwide. The observational phase was over, but the analytical phase entered a deep, critical review. Data teams spent the 5 weeks rigorously recalibrating every spectral line, rechecking every geometric consistency, and scrutinizing every anomaly discovered during the flyby, determined to establish the integrity of the data gathered before the blackout. The silence from the instruments was deafening, but the activity in the laboratories was frenetic. This period of forced waiting was essential for cooling the heated speculation and ensuring that when Atlas reappeared, the scientific community would approach the data with maximum rigor and clarity. The time was used to prepare the observatories like surgeons before a critical operation. Instruments were recalibrated, filters were tuned, and observation sequences were cued down to the millisecond. Every exposure following the reemergence would count. Every photon would be crucial. Philosophically, this vanishing act provided a powerful metaphor for the essence of scientific discovery. The universe had drawn a curtain across the stage of revelation, forcing humanity into a period of reflection and restraint. The object's absence only amplified its presence in the global consciousness. We, a species only recently capable of touching our neighboring worlds, now waited for a visitor that might have crossed light years to reach us. The forced blackout intensified the philosophical tension between the known and the unknown, between the technical precision of our instruments and profound, humbling mystery of the object's true nature. The wait itself became a part of the story, an acknowledgement that discovery is not just about observing light, but also about surviving the surrounding darkness. The world held its breath, waiting for December, when Atlas would step back into view and offer a second chance for humanity to listen to its silent, interstellar narrative. As the solar occultation neared its end, the scientific community prepared for the reemergence of 3 Eyes/Atlas by focusing its collective attention on 4 critical questions, each one representing a potential turning point in the understanding of interstellar matter. The data Atlas would provide upon stepping out from behind the sun would either resolve the existing paradoxes or deepen them irrevocably, potentially rewriting everything known about objects born outside our solar system. First, will Atlas's brightness change? A significant alteration in brightness, a sudden flare or an unexpected dimming, would be a key indicator of its internal composition and stability. A flare could signify fragmentation, surface volatility, or an internal energy release, phenomena that will reveal whether the object is a loosely bound clump of porous ice, a solid core of rock, or something engineered. Conversely, a substantial dimming could suggest a structural breakup or complete dissipation. Any major change would force a re-evaluation of its mass and composition models. Second, has its trajectory shifted? The most crucial dynamic check would be to see if Atlas maintained its purely gravitational path. A significant deviation would indicate that non-gravitational forces are at play, perhaps asymmetric outgassing jets, electromagnetic propulsion, or the influence of solar radiation pressure beyond current models. Any measurable change in its flight path would challenge the dynamically dead paradox and open the door to radically new interpretations of its behavior. Third, will it show structural breakup? The question here is not just whether it fragments, but how it fragments. If Atlas splinters into regular geometric fragments, or if it maintains a precise, non-random coherence despite the intense thermal stress of perihelion, scientists may be forced to consider a new category of celestial object, one that is neither strictly comet nor asteroid, but a composite or potentially even an engineered structure designed to withstand stellar heat. Irregular, random fragmentation would confirm it as a fragile, icy body. Fourth, what will its spectral fingerprints reveal? The final, decisive moment would be the reanalysis of its light. Those mysterious spectral emission lines, the dominance of nickel over iron, the high ratio of carbon dioxide, and the lingering possibility of forbidden green light, must either resolve into a coherent natural explanation or stand as irrefutable evidence of physics unaccounted for. This analysis would determine if the anomalies were artifacts of the initial observation or genuine properties of the interstellar material. Each of these questions represents a window into a deeper mystery, a test of the hypotheses generated during the intense flyby. The observatories worldwide prepared with surgical focus, tuning every instrument and setting every exposure sequence to capture the critical data flow. The anticipation was not just scientific, it was philosophical. The information Atlas would bring when it emerged from the sun's blinding light would determine whether it remained a scientific enigma or became an historical revelation about the composition and activity of matter beyond our cosmic home. The totality of the strange, contradictory evidence surrounding 3I/Atlas, the forbidden chemistry, the dynamic defiance, and the alignment with the wow signal, pushes the investigation to the boundary of science and imagination. The object is no longer a simple comet. It is a paradox incarnate, daring humanity to climb the scientific ladder of explanation while simultaneously whispering tempting, radical suggestions that lie just outside the realm of established physics. The core intellectual conflict revolves around its true identity. Is it a relic of ancient, exotic stellar chaos, or a deliberate messenger carrying a technological signature? The relic hypothesis is firmly rooted in physics. It suggests that every anomaly, the $CO_2 richness, the lack of water, the nickel over iron ratio, can be explained by assuming Atlas originated from a stellar system that was fundamentally different from our own. Perhaps it was born around a massive star that enriched its planet-forming disk with heavy elements, or it was ejected from the system at a very early, cold stage of formation. Under this hypothesis, Atlas is an object of profound scientific value, a pristine sample of exotic, deep space chemistry that has journeyed across a galaxy, a frozen piece of another star's birth. Its strange behavior is merely a demonstration that nature is far more diverse and imaginative than the models built only on the evidence of our local solar system. The alignment with the wow signal, in this view, is merely a profound, low-probability coincidence. The messenger hypothesis, however, forces scientists to engage with the idea of alien technology. The precise, unperturbed flight path, the contradictory sunward jet, and the haunting wild signal alignment fuel the possibility that Atlas might not be a natural body. Could it be a relic of ancient technology, a durable probe designed to withstand the rigors of interstellar travel, perhaps utilizing some form of unknown propulsion that masks its non-gravitational movements? The dynamic deadness and the high metallic content could be explained that the object is hollow, shielded, or actively controlling its trajectory. While this hypothesis is inherently speculative and risks spiraling into pseudoscience, the scientific integrity requires that researchers explore every possible explanation, especially when the natural explanations fail to fully account for the observed facts. The challenge of the scientific community is to maintain rigorous discipline while simultaneously allowing for profound wonder. Science demands that every piece of evidence must be repeatable and consistent with known laws. The moment a scientist declares something artificial, they cease to be a physicist and begin to engage in philosophy. Yet, the history of science demonstrates that every major paradigm shift began with the dismissal of an anomaly. Atlas exists in that crucial electric space between the two, a physical object that forces humanity to confront not just the known laws of physics, but the limits of its own imagination. The question is not simply what is it, but are we wise enough to recognize what it is, even if it defies the very definition of natural? The investigation into 3i/Atlas has taken humanity on a dizzying journey, from the lone geophysicists on Earth to the robotic sentinels orbiting Mars, to the deepest paradoxes of chemistry, dynamics, and historical coincidence. The object, now emerging from behind the sun, represents a final, profound test of humanity's scientific maturity. Every piece of contradictory evidence, the green light without carbon, the nickel over iron ratio, the unperturbed flight, and the haunting alignment with the wild coordinates, has converged to pose a question that pierces the core of our existence. Are we studying the universe, or is it studying us? The scientific imperative remains to explain Atlas using only the laws of nature. The next wave of data will either resolve the spectral and dynamic anomalies into a coherent natural history, confirming that the object is a strange yet natural visitor from a distant stellar forge, or will solidify the contradictions, leaving us with undeniable evidence that our models of astrophysics are incomplete. Science is not built on belief. It is built on evidence, rigorously verified and wrung out on the anvil of repeatability. The greatest value of Atlas is not in what it is, but in the sheer scale of the fundamental scientific questions it forces us to confront. Yet, the philosophical weight of the messenger hypothesis lingers. The sheer coincidence of the wow alignment, the dynamic precision, and the alien metallurgy invite the profound reflection that perhaps this object is not merely visiting us, but returning to a region it or its progenitors marked long ago. Could Atlas be an ancient, resilient technological relic, drifting across the galaxy as a silent testament to a civilization that preceded us by millions of years? The cosmos offers us this profound possibility, forcing us to observe not only with our precise instruments, but with the full, expansive power of our imagination. The ultimate truth is yet to be determined, but the process of discovery is a collective triumph. It began with an open data revelation, was verified by a global network of citizen scientists, and is now being pursued by the world's most advanced space agencies. Atlas has forced a collaboration, a shared curiosity, and a unified sense of wonder. Whatever story it tells when it steps back into view, it will leave us with a more profound question than before. Are we truly alone, or are we finally beginning to see the evidence of others? We stand at the base of the ladder, daring to climb toward the truth. The journey of 3i/Atlas is far from over. The critical data is about to arrive, and its analysis will determine whether this object remains a scientific enigma or becomes an historical revelation. What do you believe the new data will reveal? A cosmic coincidence, or the first deliberate whisper from the stars? Leave your thoughts, theories, and questions in the comments below. If this deep mystery fascinates you as much as it fascinates us, don't forget to like, subscribe, and join us as we follow the light of discovery wherever in the universe it may lead.